A current-carrying conductor placed in a uniform magnetic field experiences some force. The magnitude of this force is determined by using the formula F is equal to BIL sin theta, where theta is the angle between the direction of the magnetic field and the direction of current. The direction of the force acting on the conductor can be determined by using Fleming's left-hand rule. According to the rule, when we stretch the thumb, the index finger and the middle finger on the left hand in three mutually perpendicular directions, if the middle finger indicates the direction of current in the conductor, the index finger indicates the direction of the uniform external magnetic field. Then, the thumb indicates the direction of the force on the conductor. Now, let us discuss the forces acting on a rectangular current-carrying loop when it is placed in a uniform magnetic field. Consider a rectangular loop PQRS of length L and breadth B placed in a uniform magnetic field in such a way that the plane of the loop is parallel to the magnetic field. Connect the rectangular loop to a battery as shown, such that the current in the loop is along the direction PQRS. Let B be the magnetic induction of the uniform magnetic field between the two magnets, and I be the constant current passing through the rectangular loop. To simplify the understanding of the topic, we neglect the ends of the loop from where the current enters and leaves the loop. The magnetic field exerts some force on the arms of the current-carrying rectangular loop. The direction of current in the arm PQ of the loop is perpendicular to the direction of magnetic field. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1 is equal to BIL sin 90, which is equal to BIL, where L is the length of the arm PQ. Let this be equation 1. Here, the direction of the force is determined by using Fleming's left-hand rule. Stretch the three fingers of left hand in three mutually perpendicular directions. Here, the direction of the magnetic field is from north to south, represented by the index finger of the left hand. The direction of current is from P to Q of the rectangular loop, represented by middle finger, and the direction of thumb represents the direction of force acting on the arm PQ of the loop. That is, the force is acting downward with respect to the plane of the loop. The direction of the current in the arm QR is parallel to the direction of the external magnetic field. This implies that the angle between the direction of the current in QR and the direction of the magnetic field is 0 degrees. Sin 0 is equal to 0. Hence, the magnitude of the force acting on the arm QR of the rectangular loop due to the magnetic induction B is F2 is equal to 0. Let this be equation 2. The angle between the direction of the current in RS part of the loop and the direction of the magnetic field is 90 degrees. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3 is equal to BIL. Let this be equation 3. Here, using Fleming's left-hand rule, we find that the force acts upwards with respect to the plane of the loop. The angle between the direction of current passing through the arm SP of the loop and the direction of the magnetic field is 180 degrees. Sin 180 degrees is equal to 0. Hence, the magnitude of the force acting on the arm SP of the rectangular loop due to the magnetic induction B is F4 is equal to 0. Let this be equation 4. We observe from the equations that the magnitudes of F1 and F3 are equal. As they act on the loop in opposite directions, they are unlike forces. Hence, the net force acting on the body is 0. As the two forces F1 and F3 are non-collinear and are separated by the perpendicular distance b, which is equal to the breadth of the rectangular loop, they result in turning the loop. These two forces cause the rectangular loop to rotate about an axis that lies in the plane of the loop, parallel to its length and passing through its center. Thus, the axis of rotation of the loop passes through the midpoints of QR and SP. The magnitude of the torque τ1 due to F1 is equal to the product of F1 and the perpendicular distance between the point of application of F1 and the axis of rotation. This gives τ1 is equal to F1 into half of B. Similarly, the magnitude of torque τ3 due to F3 is equal to F3 into half of B. The net torque on the loop τ is equal to the sum of τ1 and τ3, which is equal to F1 into B by 2 plus F3 into B by 2. But F1 is equal to F3 and both are equal to BIL. Then, τ is equal to BIL into B by 2 plus BIL into B by 2, which is equal to BI into LB. As L into B is equal to the area of the rectangular loop A, we can denote the torque acting on the rectangular current loop τ is equal to BIA. The net torque on the loop tends to rotate it in the anti-clockwise direction when viewed from SP side of the loop. We know that torque is a vector. Hence, the expression for torque on the rectangular current carrying loop placed in the external magnetic field can be represented using vectors. We know that magnetic induction B is a vector. We now assume another vector A called the area vector. The direction of the area vector is given by right-hand rule. If the right hand is stretched and the four fingers of the hand curl in the direction of the current in the loop, then the thumb, which is extended out, indicates the direction of the area vector. Hence, the direction of the area vector in this case points into the loop when we observe it from top, such that the current in the loop is in the clockwise direction. If theta is the angle between the two vectors, then the torque on the loop is given by the cross product IA cross B, whose magnitude is equal to IAB sin theta. We now define a new vector, magnetic moment, denoted by M, which is equal to the product of I and A. Thus, the direction of M is the same as that of the area vector, and its SI unit is ampere meter square. Hence, torque on the current carrying rectangular loop is given by the expression τ is equal to M cross B, and hence, the magnitude of the torque on the loop is given by MB sin theta. In this case, the angle between the magnetic moment and the magnetic induction is 90 degrees. As sin 90 is equal to 1, the torque on the loop is the maximum. Now let us consider another case where the magnetic moment makes an angle theta, other than 90 degrees with the direction of the magnetic field. That is, the angle between the directions of the area vector and the magnetic field is other than 90 degrees. When the current passes through the rectangular loop, the magnetic field exerts some force on the sides of the rectangular loop as discussed earlier. Here too, the angle between the direction of current through PQ and the direction of magnetic field is 90 degrees. Hence, the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1' is equal to BIL. Let this be equation 5. Here, using Fleming's left-hand rule, we find that the force acts downwards in a direction perpendicular to the plane containing B and I. In the case of arm QR, the length of the arm QR is not perpendicular to the direction of the magnetic field. Area vector makes an angle theta with the magnetic field. Hence, the angle between the magnetic field and the current through QR is 90 minus theta. Then, the force on QR, part of the loop due to the magnetic field, is F2' is equal to BIB sin 90 minus theta, which is equal to BIB cos theta. Let this be equation 6. The direction of force F2' is obtained by using the right-hand rule. When the four fingers of a stretched right hand curl from the direction of current in QR towards the direction of magnetic induction B, the thumb indicates the direction of the force on QR. Thus, the force F2' acts perpendicular to the plane containing I and B, outward of the loop along its axis of rotation. The direction of current through the arm RS of the loop is perpendicular to the direction of magnetic field. Then, the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3' is equal to BIL. Let this be equation 7. Using Fleming's left-hand rule, we find that the force acts upward in a direction perpendicular to the plane containing current and magnetic field. The direction of current through the arm SP of the loop makes an angle 90 minus theta with the direction of the magnetic field. Then, the force acting on the SP due to the magnetic field B is F4' is equal to BIB sin 90 minus theta, which is equal to BIB cos theta. Let this be equation 8. The direction of force F4' is obtained by using right-hand rule. When the four fingers of a stretched right hand curl from the direction of current in SP towards the direction of magnetic induction B, the thumb indicates the direction of the force on SP. Thus, the force F4' acts perpendicular to the plane containing I and B outward of the loop along its axis of rotation. We observe that the forces F2' and F4', which are equal in magnitude, act along the same line, that is, along the axis of rotation. Hence, they are collinear. But they are unlike as they act in directions opposite to each other. Hence, these two forces cancel each other and their resultant is 0. Thus, these two forces do not constitute torque. On the other hand, the forces F1' and F3', which are equal in magnitude, act in opposite directions to each other and are not collinear. Therefore, the resultant of these two forces constitutes torque on the loop. The net torque acting on the loop tends to rotate it in the anti-clockwise direction when viewed from PS. The magnitude of torque due to F1' is equal to the product of force and perpendicular distance between F1' and the axis of rotation of the loop. Let D be the perpendicular distance between the force F1' and the axis of rotation of the loop. as the angle between the area vector and the magnetic field is theta. From the geometry of the figure, the perpendicular distance d between the force F1' and the axis is equal to b by 2 into cos 90 minus theta, which is equal to b by 2 into sin theta. Thus, the torque towed 1' on the loop due to F1' is equal to F1' b by 2 sin theta. Similarly, the torque towed 3' on the loop due to the force F3' is given by tow 3' is equal to F3' b by 2 sin theta. Hence, the net torque tow dash on the loop is given by the sum of tow 1' and tow 3'. This is equal to F1' b by 2 into sin theta plus F3' b by 2 into sin theta. But F1' is equal to F3' and both are equal to BIL. Then, tow dash is equal to BIL b by 2 into sin theta plus BIL b by 2 into sin theta. Replacing L into B with area of the loop A. The torque on the loop tow dash is equal to BIA sin theta. So far, we have learnt about the torque on a current-carrying rectangular loop placed in an external uniform magnetic field, in the case where the area vector makes an angle other than 90 degrees with the direction of the magnetic field. On rotation of the loop about its axis, due to the torque on it, if the angle theta tends to 0, perpendicular distance between the forces tends to 0, and this results in 0 torque on the loop. Also, while the angle reduces to 0, the value of sin theta becomes 0, which results in 0 torque on the loop.